types of the signals. There are essentially two types of the signals, analog signals and the digital signals. Well, what is an analog signal? Analog signal is a set of discrete time signals and continuous time signals. Digital signals are analog signals which pass through a quantizer. So our definitions are clear. Definitions are: analog signal is a signal which is a set of discrete time signals and a continuous time signals. Digital signal is an analog signal. Digital signal is a signal which is passed through a quantizer. And what do we mean by quantizer? And we'll get to know. Well, I want you to understand a simple flow diagram for the better interpretation of these two concepts. Well, let's suppose I am analyzing a voice signal, which means a voice is falling. Let's idealize situations right now, as I have told in the second video lecture of importance of idealizing the situations. I am now taking for the deterministic signal case. Why it's so? Because first of all, we need to understand something more than just signals itself. So I am simplifying one case to better understand what we are intended to understand. I want you to understand a graph, and let's suppose anything, signal might be anything. So let's suppose I am measuring a voice signal. Well, you see, when I am talking, most of the times it is an analog signal, which means maybe I have some pauses between one phrase and another phrase. It doesn't matter. Within the one phrase, at least within the one phrase, the signal is continuous. There is no breaks in my voice, isn't it? So, which means the signal is a continuous time signal. The moment we know the signal is a continuous time signal, we can directly say the signal is an analog signal. Alright, so voice signal is an analog signal, and let's suppose, and it will never happen, but let's suppose for this instance it is sinusoidal in nature, and I have passed this voice signal to a sampler. Well, for those of you who don't know what is a sampler is a system which basically acts like a switch, which means it picks up the samples from the signal. A continuous time, if there is a continuous time signal, let's suppose I don't want all of the values of the signal at all of the instances. Maybe I just want a t equals to t1 only, a t equals to t2 only, a t equals to t3 only, isn't it? Maybe a change is happening in the real world, and I don't want all the information. I just want what is happening at that particular instant of time, isn't it? Which means I am picking up the samples instead of transmitting all of the information, and it becomes very efficient. Sampling is a very important in communications and analog signal processing as well, and you will get to understand. But for this instance, you just have to remember sampler is a system which will pick up samples from a continuous time signal. I am repeating again. There is a continuous time signal. I don't want all the samples, I just want some of the samples, which means there is an event happening in the real world. I don't want all of the information about the event, I just want some of the information, which means at particular t equals to 10 a.m. what is happening, at t equals to 11 a.m. what is happening, and I don't want the information between the t equal to 10 a.m. and t equal to 11 a.m. I am only interested at the information at t equals to 10 a.m. at t equals to 11 a.m. isn't it? So this is called sampling. So this system, you can design a circuit as well, and this system is called sampler. Alright, and you pass it through the sampler, and obviously from the nature of the sampler itself, we are very sure that we are not going to get a continuous time signal. It has to be discrete time signal. What is discrete time signal? Discrete time signal is where signal cannot exist at each and every particular point of time, which means at t equals to 1 second signal can exist, at t equals to 2 second signal can exist, t equal to 3 second signal can exist, but it can't exist between 1 and 2 and 2 and 3. Is that clear? It can't exist between 1 and 2 and 2 and 3. Alright. Discrete time signal is essentially a sampled version of an analog signal. Alright. Discrete time signal is a sampled version of analog signal, which means what I will get. at t, let's suppose at t equals to 1 second, t equals to 1 second, I have this amplitude, let's call it A. So I'm just picking up, I'm pretty bad at drawing, please pardon me for that. At t equal to 2 seconds, I have minus A. I have minus A. At t equals to 3 seconds, and again I have plus A, let's suppose. I'm just picking up the samples randomly, there is no, pattern you have to follow, alright? A and minus A. There is a discrete time signal. Can I call this signal as an analog signal? The answer is yes. Because what is the definition of analog signal? The set of discrete time signals, or it can be a discrete time signal, it can be a continuous time signal. You can still call this signal as an analog signal. Okay? Until and unless you don't touch the amplitude, you don't touch the y-axis, you will get to know more about that in the later on of this video lecture. Until and unless you don't touch the y-axis, until and unless you don't interfere with the amplitudes, you don't make decisions on the amplitudes, the signal is still an analog signal. So, I mean, and another important question is, can I pick up samples everywhere? No, you cannot pick samples at your wish. There is a condition, because at the end of the day, maybe I sample the signal. Communication systems intended to reconstruct the signal back. To reconstruct that, you have to have some kind of law, which is called Nyquist law. You'll get to know in the later parts of the video series. So until and unless there is no decision on the y-axis, I cannot say the signal is a digital signal. So this is an analog signal and this is an analog signal. All right. And the amplitude can exist, and I'm bringing down all those. I'm trying to unify all those ideas to a single idea. How do you judge? Let's suppose you have a signal. Maybe it's a discrete time signal or continuous time signal. How do you judge a signal? You look at the signal. How do you judge a signal and say whether it is analog or digital? The only thing you have to check is you check for the amplitude. If amplitude can exist in each and every point of particular time, which means 2 volts, 2.5 volts, 2.2 volts, 2.3 volts, whatever, amplitude have to exist at each and every point of y-axis, which means, you see, discretization, we have passed it through a sampler, only at some particular point of time, the signal is existing, isn't it? So, this is called discretization of time axis, which means signal cannot exist between t equals to 1 second to t equal to 2 seconds, t equal to 2 seconds to 3 equal to 3 seconds. Signal cannot exist between these two time instants, and this process is called discretization. Until and unless we don't have a discretization on y-axis, you always call the signal as an analog signal, alright? Which means there is no decision on the y-axis. Here itself, I don't have any decision on y-axis, I'm just discretizing the x-axis, I'm just discretizing the time axis, okay? And well, coming to the digital signal, you see, digital signals are signal with much more human intervention, which means we don't want to be a signal in its raw form. Well, we have as we have seen earlier, we have a voice signal for this particular instant. I pass it through a sampler, which means I am discretizing the time axis. So I got a signal like this, alright, which has its own amplitude, and I'm passing it through a y-axis discretizer. Y-axis discretizer. You cannot call it y-axis discretizer. It is called quantizer. So we are discretizing the amplitude. Quantizer, which means I have a digital signal right now. And I have a discrete time signal. It is still an analog signal. You pass it through a quantizer. The outcome of the quantizer is a digital signal. Yes, sir? Digital signal. Okay. And how digital signal will looks like? We'll take up an example. Well, you see, digital signal is a signal which has discretization on its y-axis. The moment I say the word discretization, I have to define a condition, isn't it? In earlier case, we have converted an analog signal, a continuous time signal, to a discrete time signal. So the moment I have discretized it, you have to recall the things where I took t equal to 1 second, t equal to 2 seconds, t equal to 3 seconds, which means I'm putting a condition. I'm intentionally putting a condition that I am intended to pick the samples at integer time instants only. So I have defined a condition before discretizing. It might be the y-axis, it may be the y-axis, it may be the x-axis. I have defined a condition to discretize the things. So in sampler, we are discretizing the time axis. In quantizer, we are discretizing the amplitude axis. So I have to make a decision, which means I have to if there is no decision, if there is no discretization as well. If discretization exists, it means that there is a decision. So what is my decision? I want to have amplitude should be either 0 or 1. Amplitude might be either, this is just an example. You can extend it further. Condition is something that you can write. There is no law on that. This is something you define. So you can write it like this. 0, it can be 0, it can be 1, and it can be 2, and it can be 3. So amplitude can be only the integers, cannot be so amplitude cannot have the decimal number, which means if amplitude have 1.2, it is a quantizer. If amplitude is 1.2, I cannot have 1.2 at the output of the quantizer, isn't it? Because what is the work of the quantizer? It has to make a discrete time signal into a digital signal, isn't it? So the amplitude is 1.2. I am giving this input to the quantizer, so amplitude cannot be 1.2, of course. So I need to put I have a condition now. It can be 0, it can be 1, it can be 2, and it can be 3. So I will map 1.2 its nearest possible values. So what is the nearest possible value for 1.2? 1, isn't it? Because if 2, the difference between 2 and 1.2 is 8. And the difference between 1.2 and 1 is what? 0.2, isn't it? So what is the nearest possible distance? 1 is the nearest possible thing. So 1 is output. Let's suppose 1.22. Then what will happen? Same thing, isn't it? 1 is output. 1.03. 1 is output. 1.04. I want you to observe this carefully. 1.05. 1 is output. Which means, you see, for how many values I can map, the question is how many values that I can map to 1, that is the question. How many values can be possible so that quantizer can map the signal into 1? The answer is infinity, isn't it? Because the number of real numbers between 1.01 and 1.02 itself is infinity, which means what we are doing, I want you to understand this, what we are doing, we are mapping infinite set of points to a single point. Alright? Which means I have a pool. I have real number 1.01, 1.02, real number, set of real numbers 1.03, 1.04, maybe 1 is also another case, isn't it? 0.99, 1.034, etc. Which are near for 1. I'm only taking the case of the values which are nearer to 1, so that quantizer can make the decision to equal to 1 to simplify the things. Yes. And I am mapping all the values to a single point. Alright? So what is a quantization now? Quantization is basically, when you look at deeply, the definition of quantization is quite different, isn't it? Quantization is nothing but we are making a decision, even though I don't care, even though the value is 0.99 I don't care, even though the value is 1.00 I don't care, even though the value is 1.03 I don't care, until and unless it is nearer to the 1, I will map it to 1. So I don't have to think about all the numbers, 1.01, whether it is 1.01, whether it is 1.02, maybe I've got some error, 0.001, I don't even think about that. I have a set of values which will map to eventually 1. So all I have to think about is 1. So what we are doing essentially here, we are simplifying the things, isn't it? There is simplification. Until unless, let's suppose you have a gigantic set of values, you have thousands of values, you have hundreds of thousands of values. Is it easy to handle hundreds of thousands of values, or is it easy to handle one value? Obviously, it is quite easy to handle one value. Well, I have another question for you. If we are mapping all set of values 1.01 to 1, 1.02 to 1, 1.03 to 1, all of the values to one single digit, aren't we losing some information? The answer is yes, we are losing some information. That there is an information loss which cannot be reconstructed back, but that information loss should be within the tolerable range, isn't it? Because we are defining, right, isn't it? If I map 99 to 1, that is catastrophic. That is something that you cannot do. Alright, I am mapping 1.01 to 1, so the error is fair enough. So that information loss can be tolerable. Alright, so what are the takeaway points? What is an analog signal? Analog signal is a continuous time signal. A signal which has much less of human intervention, which means the time axis is continuous, the amplitude axis is continuous. Then we call that signal as an analog signal. What is a discrete time signal? Discrete time signal is a signal which we got by passing a continuous time signal through a sampler. What does sampler do? Sampler discretizes the time axis. And what is a digital signal? Digital signal is a signal which we got by passing a discrete time signal through a quantizer. So what we are trying to do in quantization, we're intentionally introducing some error, isn't it? Aren't we introducing some error? We are mapping all those values to a single value. So aren't we introducing some error? Obviously we are introducing some error. But what is the gain we are getting? Instead of handling the gigantic values, we will still simply handle with one value. Well, maybe this kind of reason will be more raw for you, but later on in your course you will realize the technical details of the technical importance of the quantization. You will get to know that. Okay, and that's it for this video.